Hello guys, welcome back to MedZone African Motives. Still on our power machines and 5 revisions. This time we just want to focus on the combustion of fuels by mass. In this case, when you're considering or when you're given a certain mass of a fuel, but considering what we refer to as hydrocarbons. In this case, hydrocarbons coming from the combustion that is happening between we are just focusing with the hydrogen and carbon. These are the ones that we are focusing, hydrogen and carbon, or carbon and hydrogen. That is from hydrocarbon. So we do not have things like sulfur. It's not part of this combustion. The sulfur part is the one that work it on our previous part. So in this case, you'll be given a combination or a scenario whereby you are given this in the format of CX multiplied by HY, or just CX HY, okay, whereby C is for the carbon, and this is the number of carbons that we have, the H for hydrogen, the number of hydrogen that we have. So it's not something that is supposed to be difficult. Like here, we are simply, let us refer, if you check on the process whereby maybe you are dealing with methane, it's another part that you're going to be considering, or any part that you be given. So you'll be given in this format, all right, where X is just a number to be given, and also Y there is a number, just like here. On this question that we are going to consider, we are given a liquid fuel, which is given as C7H18. You do not need to know the name of that fuel that you are given there. There is nothing important about you knowing the name, so do not be troubled about that. What is important to know the number of carbon that we are having, the number of hydrogens that we are given in this case. This gives us the value of X and the value of Y in this case. All right, so this is the fuel that you're given of 1 kg mass with 40% excess air in this case. So take note, we are dealing with the 40% excess air for this to give a complete combustion, or to completely burn this part. So the atomic masses of these elements are as follows. So the elements that you are considering is hydrogen and carbon and also oxygen. So these are the atomic masses that we are given, and also assume that this is a consideration that you are supposed to know. You are not even supposed to assume. You are supposed to know this, that by our syllabus, A is going to be consisting of 23% of oxygen, 77% of nitrogen, but this is supposed to be by mass. If we are given a condition whereby we are dealing by volume, we shall have a different condition in terms of our percentages. This will be taken to 21% of oxygen and 79% of nitrogen when we are dealing by what? By volume. So this is something that you're supposed to know. It's not every condition that you are given. So that's why I'm saying you're supposed to know this part for each and every part. So that is the constituents that is building up the air in this case. It is being built up of 23% oxygen, 77% nitrogen by mass. So the question of 5.1 was to find the theoretical mass of air required for complete combustion of what? A 1 kg. We are referring to 1 kg of the fuel, and we are dealing with the theoretical mass. I want you to check from your formula sheet here so that we can be together. If you consider the first part, we talked about this formula, or the application of this formula, which is true. This was on a consideration where you are not dealing with hydrocarbons. There you can see we are talking of sulfur being there. When we are dealing with the hydrocarbons, this is the formula that we are going to apply, or the formula that we are going to use in order for us to obtain the theoretical mass of what? Of air in this case. So I'm going to present this formula, then we talk about this. There's a lot that you are supposed to consider on this formula on your answering of the question. So here we are going to take our fuel, liquid fuel, which is C7H18. All right, so this is what is important on that part alone so far. So that's 5.1. Remember, we are given this as C7H18. So this is what you are going to have from our formula. The one that we are given as CX HY plus X plus y over 2, in this case, y over 4, all right? And this is O2, which is our oxygen, should give us, in this case, we can just write is equal to, or you can just say it must give us X times the carbon dioxide. So here shall we have carbon dioxide plus y over 2 H2O. So you're just taking the formula that you are given from the formula sheet. This formula that we are seeing here, it is giving us the value of X. Remember, I said this must be given in a format of CXHY. So you don't even need to understand or to know the name of the fuel that you're given, the liquid fuel. What you need to understand is that the X is representing the number of carbon that we have seen. So the X there is a 7. So that is important. X there, it's a 7. Y is represented by 18. So Y simply is equal to 18. So what it means, wherever we are seeing X, wherever there is X and Y, we are going to substitute these values as they are. So if you are to substitute, what you will need is to find the theoretical mass of air. Remember, why using this formula? Because we understand that the theoretical mass of air, I explained this way, that we can have the mass of air from, all right, let's just say theoretical so that we do not confuse each other. Theoretical mass of air in this case. This can be taken from the percentage that in terms of, because we've got oxygen, remember by mass, oxygen consists of 23%. That is oxygen, it is taking 23%. So, and air consists of both oxygen and nitrogen together combined, that it must be at 100% of both. Because these two sections, they are taken out of air. Remember, nitrogen, we said it's going to be at 77%. That is when you're dealing with nitrogen. So it's a constituent that is giving, or that is building up the air. So if it is built up with these two, what does it mean? It means that out of the oxygen that we have, which carries 23%, the air, which is at 100%, is going to be out of the 23% of oxygen in this case, which is the mass of oxygen. That's why you see on this formula here, they give it this way. I want you to understand also this formula. It's not important of this part, but I want you to understand also this scenario that you are given, or the formula that you are given here. This 100 over 23 is the one that I'm explaining. If you see here, they write 100 over 23. What is it? It's from the oxygen. So this whole part that I indicated, I indicated on this part to say the mass of air, the theoretical mass of air in this case is going to be 100% over 23% times the mass of oxygen. So it simply means on your formula here, where we are given, we're supposed to have 100 over 23 like this, times the mass of what? The mass of oxygen. So what it means is that this whole part that we are seeing here, this whole part here, this whole part is representing the mass of oxygen. This whole part that we see is the mass of oxygen. So here you have it on the formula, but on this part, we are supposed to take it from the formula that we are given, which is from the oxygen here, from this oxygen. So meaning to say, we are going to apply the same concept to say, this theoretical mass of air is supposed to be 100 over 23 times the mass of what? The mass of oxygen in this case. We're going to use the mass of oxygen. So the question is, how are we going to obtain the mass of oxygen since we are supposed to use 100 over 23% of oxygen? All right, we can substitute our values, X and Y, as they are in our formula. So it's going to be C7, H18 plus X in this case. Remember our X is 7. So this is 7 plus Y in this case, which is 18. So it's going to be 18 over 4 of O2 like this, which is going to give us, or you can just write is equal to, which is fine. Then X there is 7 of the carbon dioxide plus Y over 2, Y is 18, so it's going to be 18 over 2 of H2O, which is our water in this case. All right. If we were to simplify, guys, we're going to obtain this part. There's nothing that you're going to have for now. I shall explain in the later stage. All right, you simplify this part, you obtain your value. This was going to be 11,5, something like that. From this part, if we simplify here, direct, we're going to obtain 11,5. So I want to just also be with you what I'm trying to say. We can just simplify this part. Some of us, I've seen that the use of calculator is still challenging us again. So here, this is supposed to be 7 plus 18 over 4 like this, 18 over 4 like this, which is going to give us 11,5. All right, so that's the part that I'm explaining there. So we're going to obtain 11,5 as per given value. So that's 11,5 O2, which is going to give us 7 CO2 plus CO2 salt. Then you've got 9 H2O, which is our water from the carbon dioxide. All right. The question is, when you are at this stage, you are very tempted, very, very much tempted to say, I am having the mass of each. No, this is wrong. At this stage, you are supposed now to obtain the mass from the atomic masses that we are given. That is why you see we have, or we are given the atomic mass. It's not like in each and every question you are going to be given, you are supposed to know the atomic masses by heart. The atomic mass for hydrogen, for oxygen, for carbon, we are supposed to know those ones by heart. So if we are to check here, yes, they played a role this time to give us, we are given hydrogen 1, oxygen 16, and carbon, which is what? Which is 12. So we are going to substitute so that we obtain the mass now, which is, we are now substituting our atomic values that we are given, which is the atomic masses. So here we're going to multiply by the prefix. So it's 7. Here it's going to be 7 times the carbon. So according to carbon, we've got 12. Remember, carbon is 12. So it's going to be 7 times 12. Then we add to the hydrogen. There are 18 of them times the atomic mass of hydrogen. Remember, the atomic mass of hydrogen, it's 1. So this whole combination, it's a single term, which is going to give us the mass that is corresponding to what? To the fuel that we are given. We do the same thing for the oxygen that we have here. We are having our oxygen. So this is going to correspond to the oxygen, which is going to be plus 11,5 already, this one. So this is going to multiply whatever that we are going to obtain from our oxygen. So that's our prefix here is 2 times, remember oxygen, it's 16, or if you do not know this, as here we are given oxygen, there is 16, but you're supposed to know these ones by heart. All right, so that's a 16 here. All right, which is going to give us that's 7. So as you can see, carbon dioxide, these, remember, these are our inputs. Remember, we are burning this fuel by oxygen. So these are the inputs that we are given. In this case, we are dealing with what? With the inputs giving us the outputs in this case. So for the outputs, we've got carbon dioxide and we've got water. These are the outputs that we are having. So we're talking about outputs, which is the products of what? Our combustion. So far, as we can see, we can tell the products. So it's a combination of carbon and oxygen. So we are going to multiply this way. 7 into carbon is just 1 here. There's a 1. So it's going to be 1 times carbon. Remember that carbon is 12. So it's going to be 1 times 12 from the atomic mass plus the part of the oxygen. Here there are 2 of them times the oxygen. Remember, oxygen we said is 16. So it's going to be 2 times 16 like this. That is this whole part, everything should be multiplied by 7. Everything that you're going to have here plus 9 again to the product of water, which is 2 hydrogen that we have. So it's going to be 2 times the atomic mass of hydrogen. Remember, it's 1 plus the oxygen. It's only 1. So meaning to say here, we are going to multiply 1 times. Remember, the atomic mass of oxygen is 16. We are substituting the atomic masses. Please, guys, know these ones by heart, because it's not always where you are given these values. Sometimes they do not even give you. You're supposed to know these values. So with this part, we are now obtaining, which are the molecular masses, which is the actual mass that we need corresponding to the what? To the fuel that we are given here. Do not combine everything. Simplify this part here. Everything from this part must give us a single term. So we are going to simplify the mass for the fuel. In this case, we are dealing with the fuel. So that is 102 plus, you simplify this part again, this whole part, you multiply it as it is, you are going to obtain 368 corresponding to oxygen. This must give us, or it is equal to, the part of the carbon dioxide. Remember, this is what we have for the carbon dioxide. This whole part here is for carbon dioxide. This whole part is for water. This was for oxygen. This was for our fuel in this case. So meaning to say, if you combine this whole part, multiply it by 7, you obtain the one for carbon dioxide, that is 308, plus, do not combine with the water. Water is on itself. So you combine it on itself, this part on its own. So we're going to combine the water on its own, and this was going to give us something like 162. Okay, I want to explain this stage because most of us have a confusion to say, why do we have to divide by 1 or 2 or this and that? Why do we have to divide by this value? This is what is happening, guys. We are taking the mass, we need the mass of oxygen that is going to burn this fuel that we are given. We need to burn this fuel to have these products here. So as it stands at this stage, it means here we've got 102 kgs of the fuel corresponding to 368 kgs of the oxygen, meaning to say we need 368 kgs of oxygen to burn 1 or 2 kgs of the fuel in order to give us this part that we have on the product, which is 308 kgs of carbon dioxide, 162 kgs of water. So we are supposed now to relate to say, okay, if these are the masses that we have, what if we are to use exactly the way they are, because here they are asking us to calculate this mass for complete combustion of a what? A 1 kg of what? Of the fuel in this case. That is where now we have to consider to say, all right, out of the number of kgs that I'm having here for this fuel, because we are having our fuel here at how many kgs? Our fuel is affecting at 102 kgs. But it's needed per 1 kg per 1 kg fuel. That's per kg of the fuel. So that's why we are supposed to divide by 1 or 2 for the fuel. Our fuel is this one. So the mass of the fuel is this 1 or 2. So if we divide by 1, the moment we divide by 1 or 2, this one gives us a 1. So we have 1 kg of the fuel now. Then we will know what is going to be the other mass for each and every part that we have. So here, in order for us to obtain 1 kg, we are going to divide throughout by 1 or 2, divide by 102 throughout each and every number that you have. You are supposed to divide it by 1 or 2 like this. This one you divide by 1 or 2, you divide this by 1 or 2, you divide this by 1 or 2, you divide this by 1 or 2. So if we are to divide properly, that means here we are going to obtain a 1. So we now have 1 kg of the fuel. And what is our fuel in this case? That's C7H18. So we now have 1 kg of C7H18, which is our fuel in this case, which corresponds to how many kgs of oxygen. So we are going to divide this part by 1 or 2. If we divide, that was going to give us something like 3,608. So that is what we're going to obtain. That's 608 kgs in this case. For what? For oxygen. We are relating to oxygen. So this is the mass that is affecting oxygen. Oxygen, remember, it is just aiding the burning or making the burning to happen. That is the combustion part. So this is going to give us, or we're just going to write is equal to, which is fine. Now we consider the mass that is going to affect carbon dioxide, which is our product there. So what is going to be the mass? We divide 308 divided by 102. That was going to give us 3,0196 and so on, which is 302. If you change that part, 9 was going to be affected to change this into a 2. So that was going to be the mass of what? Of carbon dioxide. So this is the mass affecting carbon dioxide in this case. Plus, we consider for the water in this case. For the water, we've got 162 over 102. We divide again. We were supposed to obtain something like 1,588 kgs. So this is the mass of water that we are obtaining at the end as a product. These are the products, the output. On the input, we are saying if we introduce, or if we have a 1 kg of the fuel, it is going to need 3,608 kgs of oxygen to burn completely. It must need 3,608 kgs of oxygen so that we obtain 3,02 kgs of carbon dioxide plus 1,588 kgs of water. That is what it means. So the question is, if it is like that, therefore, can we obtain, in this case, we are now asking ourselves, because if you add, even if you add this, we must obtain the same on the right-hand side. So the question there was not about having this mass of fuel, this and that. But because this formula, it carries the oxygen that we need. Remember what I explained on my formula here, that the theoretical mass of air is going to be 100 over 23 times the mass of oxygen. And this formula, it consists, or it carries of the oxygen. So if it has this oxygen, we are going to apply it now to say, okay, we know that our oxygen is taken at how many kgs? Our oxygen is taken at 3,608 kgs. This is the mass of oxygen needed for a 1 kg of fuel. So now we can calculate our theoretical mass of air. So our theoretical mass of air in this case is going to be given as what? Remember my formula, I said it's going to be 100 over 23 from the concept that the air consists of what? 23% oxygen, and we are using the mass of oxygen. That's why we have to use 23 here, because we are using what? Oxygen, but the air is at 100%. Oxygen at how many percent? At 23. So you multiply to the mass of what? To the mass of oxygen. I explained this part previously. So here we're just going to substitute. Since we have the mass of oxygen here from our formula, we are going to take that mass of oxygen, which is 3,608 kgs. This is the mass that is affecting our oxygen in this case. So if we are to simplify properly from this one, we were going to obtain something like 15,687. So that was going to be the answer there, which is the theoretical mass of air. This is not the actual mass of air. The actual mass of air, we have to consider what is going to happen with the excess air and so forth, because there's an excess air. So this is just the theoretical mass of air, which is the same mass of air that we're calculating previously using this formula, where you're asked to calculate the theoretical mass of air, then you use this formula. But this formula, it was directly giving us the mass of air direct. There are no adjustments. You are obtaining direct from those percentages that you are given. You are obtaining exactly the theoretical mass of air. But this one, you have to play around now with the mass of oxygen. Then you use that mass of oxygen now to determine the theoretical mass of what? Mass of air in this case. So that was our question. Let us consider the other part here, which is 5.2. So 5.2 now, they need us to calculate the actual mass of air. So take note now, they need the actual mass of air required for the combustion, but still at what? 1 kg of fuel. As we know that at 1 kg of fuel, we now have the theoretical mass from there. So we can obtain the actual mass from what now? From the excess that we are given. Remember, we have got a 40% excess in this case. So I'm just going to take this as X. So X representing the excess air percentage can help us now to obtain the actual mass of air, which is going to be given by this formula. So let me just help you here. So from the theoretical mass, from that theoretical mass that we have, we are going to have now the actual mass of air in this case, which is given from the theoretical mass of air. So we are going to use the theoretical mass of air in this case, this one, times, due to the excess of X, remember we've got X, which is 40%, which is our excess. So we are going to have this as 100 plus the excess air percentage over 100. The over 100 here is of removing percentage. Remember, how do you remove the percentage? You divide by 100%. So we are going to take the theoretical mass of air in this case. That means our actual air is going to be taken as the theoretical mass of air, which is the one that you're obtaining here. Remember, theoretical mass of air, we calculated, we got 15,687 kgs multiplied to 100 plus x, of which our x is 40. So if we add, in this case, 100 plus 40, that is going to be 140 in this case, percent. So it's 100% over 100%. That's why the percentage is not there. So, but we are supposed to have a percentage there. So we're going to have 140 from the sum of these two. So it's going to be 140 in this case. That's 140 over 100. All right. Sorry for that. So this is 100 over 140% over 100%. So we can obtain now the actual mass of air in this case. So this was going to give us something like 21,9618 and so on, which is 962 kgs. So if we are given a condition like this, first let's check how our question is given, because you can also write per kg fuel. Here they are saying the theoretical mass for complete combustion. If they ask us, they can ask this as per kg. You can just even write per kg fuel, which is fine because we are taking this per kg fuel. So you can even write this answer as per kg fuel, per kg fuel. That is to specify that the mass that I am having, I'm taking it per each kg of what? Fuel given. So you can even write as per kg what? Per kg fuel, which is fine. It's actually one and the same thing. Or you can just write the mass of air, because we need the mass of air, but you can even specify that I'm taking this per what? Per kg fuel, which is actually fine. So that is the actual mass of air taken from the theoretical mass of air with the excess air. Then 5.3, we are now asked to calculate the mass of each product of combustion, the mass of each product. All right. I explained that already from the formula that we have. You've got the products, some of the products, we have them. Remember what I was explaining here, outputs of the products. So we already have carbon dioxide and water on the product. These are the products that we are already seeing on this part. Let me just write them aside here so that we do not shift a lot. So already we have got these products from our formula in this case. So that is 5.3 in this case. All right. So we are going to acquire or to need the products of what? Of combustion. So from our formula, we saw that already we are given two products, which was carbon dioxide and water. These are the two products that we have. But as we know, wherever there is excess air, it becomes a product. So we are going to apply excess air in this case, which is excess oxygen. From the excess air, we are going to obtain excess oxygen, which is a percentage of excess air to the oxygen that we are given. All right. And also nitrogen being the part of air consisting of 77% by mass, it must be there. Remember, when we were calculating, we were using 23, all these calculations, guys, if we check, we were using 23% of oxygen. We're saying 100 over 23. Where is the 77%? That is the nitrogen. So it is there on our outputs, but not included on the formula. It's not there on the formula because we can take it from the mass of what? From the mass of air, since it has 77% on its own. So meaning to say, these are the products. Now we are not considering sulfur. These are hydrocarbons. We do not have any sulfur there. So meaning to say we are going to consider only these products. All right, so like I said, carbon dioxide, we are already given on the formula here. We are already given the mass of carbon dioxide here. If you check, we have got carbon dioxide already, just like what we did on oxygen. If you remember what we did here on oxygen, we took the mass of oxygen, which is 3,608. We have it on the formula. Same thing with our carbon dioxide in this case, which is the value that is corresponding to this one. We have the value of carbon dioxide here. Remember, the mass of carbon dioxide is corresponding per kg fuel. Our carbon is what? 3.02 kgs. So we are going to take that as it is. There's nothing that we're going to change there. So it's 302 in this case, right? So that's 3.02 kgs from our information, same as water. If you check here for water, we also have the mass here for water. That was the mass corresponding to water, which is 1,588. So meaning to say for water, we have the value here, 1,588 kgs. So that is the mass. What about the excess oxygen? We are now taking it from that excess that we are given, because we have, I want you to understand this skill, guys. As we have the oxygen here, the oxygen is there. This is the mass of oxygen. Taken on a normal, remember you're saying theoretical. At normal conditions, that is where we took this value, at normal conditions. But because there is another part of air that we are referring as the excess like more of what is expected, that is the excess that is we are talking about, more of what is expected. So the excess now is going to affect the oxygen on its mass, which is the mass of oxygen here. And the percentage, remember at our excess here, the percentage was 40%, all right? I was supposed to just write this aside. But if you check, our excess air was at 40%. This is the excess air. So meaning to say, we are going to use that as a percentage of what, as a percentage of air on the products here, as a percentage of oxygen, because we need excess oxygen. So we are going to take 40% of it. So this is going to be 40% from the excess air of what? Of the amount or the mass of oxygen, of which we have this mass of oxygen, 40%, that's 40 over 100, which is going to be 0.4 times the mass of oxygen that we are given. So the mass of oxygen, as we considered before from our theoretical conditions, our oxygen here, that is O2, is 3.608. So you're going to use this value. That's 3.608 kgs. So that was going to give us the mass that is corresponding to oxygen at excess, which is 1.443 kgs. All right. Then we deal with the nitrogen on our side. We're going to have our nitrogen aside. All right, remember what I said about nitrogen. It's part of air, this one, which consists of 77%. So if it consists of 77% of air, we are saying it is 77% of air. Therefore, we are going to multiply to 77%, which is 77 over 100, or 0.77 times the mass of air, not the theoretical, but the actual mass. We are talking about when it is actual. So here we are supposed to relate to the actual mass of air, not the theoretical mass whereby we are just working with normal condition. No, we need the actual mass, which is here. Remember, we had the theoretical, then we calculated the actual mass of air here. We obtained our actual mass of air per kg fuel as 21,962. So this is the value that we are going to take from the actual mass of air from our 5.2. So that is, we are simply going to multiply to 77%. Since we are saying nitrogen, it has 77% of what? The actual mass of air, which was 21,962 kgs. So multiplying this, we are going to obtain a mass of 16.911. This is the mass that you're supposed to obtain for your nitrogen in this case. All right, so we have all the products. We have listed everything in this case, carbon dioxide, water, the excess air, and the nitrogen. These are the products. Because we are going to need their corresponding percentages, it's best for us to obtain the total, because in order for you to have a percentage, you need the total for everything. So you can just write the total aside, or you can just even ignore it. Then you use it when you are calculating the percentages, or you can just indicate the total. So you add now these masses, the mass of carbon dioxide, the mass of water, the mass of excess oxygen, and also the mass of nitrogen. That was going to give us a total of 22,962 kgs. So I want you to add properly these values. This is what you're going to obtain as a total. So that is the total of everything that we have there as the product in terms of what? Mass or of any product that you're given. You have to take it accordingly. You have to take each product accordingly. All right, 5.4, that was the last part of this question, which is to calculate the percentage of each mass. That is the percentage of each mass that you're given of combustion. The product, the percentage now of each mass of combustion. The percentage that they're talking about is supposed to be from the product. We are referring from the product of combustion. That is the one that you are referring. But now we need the percentages. So as we know, guys, mathematically, if we are given a certain condition, like it's a test or whatever that you are to calculate a percentage, you need the total of that part that you are dealing with. And you consider each and every mark that is a concept, or each and every person. Maybe you are having a table or a presentation of in form of a table, whatever that you are presenting, but in terms of the percentage, in terms of dealing with the percentage, supposed to be a certain quantity over the total of given quantities that we have, meaning to say, in terms of these products, in terms of our products of combustion, we have their total corresponding. So with the total, this one corresponding to these, we are going to calculate the mass, the percentage of each and every product that we have. So that's our 5.4, which is a percentage. We are going to have percentages of what? Of combustion in this case, of our combustion, which is from carbon dioxide. We simply need what we have in terms of its mass. It has got 3.02 kgs. So carbon dioxide is taking 3.02 kgs out of how many kgs, which is the total. All these products combined together, they give us a total of 22.962. So we are going to have a percentage from there multiplied to 100%. So that's the whole condition on calculating of the percentages, is what you are calculating, which is the product over the total of everything of that combustion. So in this case, we're going to obtain the percentage corresponding to carbon dioxide was going to be 13.14. So it's going to depend. Maybe you're going to use 2 decimal place or 3 decimal place. I was using 3 decimal place. So that is going to be 0.152%. We do the same thing for water in this case. So water, according to this part, it carries 1.588 kgs. So we are going to have 1.588 kgs out of the total of all the products, which is 22.962 times 100%. So we obtain the percentage of water in this case, which was going to be 6.916%. We do the same thing for the excess of oxygen in this case. So we're going to have the excess of O2, or excess O2 in this case. We had a mass out of everything, which is 1,443 kgs out of the total. So that is what you're going to do throughout. You can even just use your calculator direct, even not to present this part, just use your calculator. So that was going to be 6.284%. And lastly is our nitrogen. Remember, our nitrogen is part of our products in this case. So we're going to consider nitrogen, which, as you can see, it is the one that is getting the bigger mass. As we can consider all the masses that we are given, it is consisting of the bigger mass in this case. Out of 22, it is carrying 16 something. So it means that is the one that is going to have the bigger percentage, also the biggest percentage of all these. So let us calculate and see. The mass of nitrogen, 16.911 over the total of everything, 22.962 times the 100%. Now we are going to obtain exactly the percentage of nitrogen, which is 73.648%. So combining these now, because we know we were taking this percentage from the total of 100%, our percentage is supposed to be related back to 100%. So it also means that we are going to obtain this total back at 100%. So I want you to add this, these percentages from carbon dioxide, water, excess oxygen, nitrogen, add everything. You must obtain 100%. That is to show that this percentage, they do correspond to each other. But now the issue is that if you are using a wrong total or maybe wrong values here, you're going to obtain exactly 100% again because you were using a wrong total. So it means it's difficult for you to actually access to say your answer is correct. By obtaining 100% does not mean that your answer is correct. Because if I just use, let's say I've got 3, I've got 2, I've got 5, I've got 7, and I obtain a total of these numbers and they are wrong messes, these ones, or you obtained a wrong answer, a wrong answer, a wrong answer, a wrong answer, a wrong answer. You are working from a wrong answers, wrong total. We are still going to obtain your 100%, but that does not mean that your answer is correct. So it means for you to access your, to assess your answer in terms of an exam condition is going to be very, very difficult, because even if you are dealing with wrong values, you still obtain 100%. So you're supposed to be careful on your calculations. Do not assess your answer by 100% to say it's yes, this one is just for verification to say maybe if I made an error on these values now, I have these values as they are, then now I make an error on my calculation. It means I'm not going to obtain 100%. Maybe I obtain something like 90 or 8 or 60. That one, it shows you that you just made an error maybe on the substitution part. So that is how maybe you can just correct from there, not to relate to say if I get 100%, my answer is correct. All right, so we are going to see similar questions as we move on, and also we are going to talk about a combustion that is going to happen, but considering by volume. Remember, this was by mass. We can consider by volume, whereby I was explaining that part to say the percentages here, they are going to even change by volume. You no longer have 23% and 77%. These ones, they only apply when it is by mass. So you're supposed to be careful also on your percentages to not to confuse them in exam in case you are not given, but they can do like that. Where you are not given these percentages, you are supposed to know them. So we will see as we are moving on.